A single AI training rack can now draw 100 kilowatts of power. 5 years ago, a typical server rack drew 5 to 8. That is a 12 to 20 times increase in heat density in half a decade. And here is the problem: the cooling systems that have kept data centers running for the last 30 years were never designed for this. Air cooling, the system that built the entire data center industry, is hitting a physical wall. There is only so much heat that moving air can carry away from a chip, and AI just blew past that limit. The industry is now in the middle of a fundamental transition. Liquid cooling is no longer experimental. It is being deployed at scale by every major hyperscaler, and it is going to reshape how data centers are designed, built, and operated for the next 20 years. Today, I am breaking down both systems, how they work, what they cost, where they fail, and which one wins. The answer is more complicated than you think. Air cooling has been the standard since the first commercial data centers in the 1990s. The principle is simple: push cold air through the servers heat the air, extract the hot air, and cool it back down. Repeat. In a traditional raised floor data center, computer room air handling units called CRAHs push chilled air into the space beneath a raised floor. That air rises through perforated floor tiles into cold aisles, passes through the server's front to back, exits as hot air into the hot aisles, and gets drawn back into the CRAH units to be cooled again. The CRRs are connected to a chilled water loop which runs to chillers on the roof or in a plant room. The chillers reject the heat to the outside environment through cooling towers or dry coolers. In cooler climates, free cooling economizers can bypass the chillers entirely and use outside air to cool the water loop directly, which dramatically reduces energy consumption. This is one of the main reasons hyperscalers build in Scandinavia, Ireland, and the Pacific Northwest. Air cooling works. It has worked for decades, and for standard enterprise workloads running at 5 to 15 kilowatts per rack, it is still perfectly adequate. But it has three fundamental limitations. One, air is a poor heat conductor. It carries roughly 4,000 times less heat per unit volume than water. To cool a high density rack with air, you need enormous volumes of it moving at high velocity, which means bigger fans, bigger ducts, bigger plant rooms, and more energy. Two, hotspots. Air does not cool evenly. The chips generating the most heat often sit in the middle of the server board, furthest from the airflow edges. Thermal throttling, where chips slow themselves down to avoid overheating, is a real performance limiter in air-cooled high-density environments. 3. Energy overhead. In a traditional air-cooled data center, cooling can consume 30 to 40% of total facility power. That is power that could be running servers instead of running fans and compressors. For years, the industry optimized around these limitations. Hot aisle and cold aisle containment reduced mixing, variable speed fans improved efficiency, higher supply air temperatures reduced chiller load. These incremental improvements kept air cooling viable through the cloud computing era. Then AI changed the equation overnight. Modern AI training clusters pack GPU modules so densely that a single rack can draw 60 to 100 kilowatts. Some next generation configurations are pushing toward 120 to 150 kilowatts per rack. To put that in perspective, a standard office building uses about 20 to 50 watts per square meter. A single AI rack uses the equivalent of an entire office floor. Air cooling simply cannot remove heat fast enough at these densities. You would need hurricane force airflow volumes to keep these chips within operating temperature. The physics does not work. This is why every hyperscaler and an increasing number of colocation providers is deploying liquid cooling. Liquid cooling comes in three main forms, and the differences matter. Direct to chip cooling is the most widely deployed. Cold plates sit directly on top of the hottest components, the CPUs and GPUs. Coolant, usually water or a water glycol mix, flows through the cold plates, absorbs the heat, and carries it to a coolant distribution unit outside the rack where the heat is transferred to the building's cooling loop. The servers still have some fans for secondary components like memory and storage, but the primary heat producers are handled by liquid. This approach can handle rack densities of 40 to 80 kilowatts comfortably. Rear door heat exchangers are a retrofit solution. A water-cooled coil replaces the rear door of a standard server rack. Hot air from the servers passes through the coil on its way out and gets cooled before entering the room. This reduces or eliminates the need for room level air cooling. This approach is popular for existing facilities that need to increase density without a full cooling infrastructure rebuild. It handles 15 to 30 kilowatts per rack, which is a significant step up from traditional air cooling, but not enough for the highest density AI workloads. Immersion cooling is the most radical approach. The entire server, bare board with no casing, is submerged in a tank of dielectric fluid, a non-conductive liquid that absorbs heat directly from every component simultaneously. Single-phase immersion uses a fluid that stays liquid throughout the process. Two-phase immersion uses a fluid that boils at a low temperature, turning to vapor as it absorbs heat, then condensing back to liquid in a condenser above the tank. Two-phase is more efficient, but significantly more complex and expensive. Immersion cooling can handle rack densities above 100 kilowatts. It eliminates fans entirely, which reduces server power consumption by 10 to 15%. It cools every component evenly, eliminating hot spots, and it operates nearly silently. The trade-off is operational complexity. Servicing hardware means draining or extracting boards from fluid. The dielectric fluids themselves are expensive and some have environmental concerns, and the mechanical infrastructure, tanks, fluid management, leak detection and containment adds design and construction cost. Here is where it gets practical. A traditional air-cooled data center at 10 kilowatts per rack costs roughly $8,000 to $12,000 per kilowatt of IT capacity to build, including all cooling infrastructure. Direct-to-chip liquid cooling at 40 to 80 kilowatts per rack costs roughly $10,000 to $15,000 per kilowatt to build. Higher capital cost, but you fit 4 to 8 times more compute into the same floor space. Immersion cooling at 80 to 150 kilowatts per rack costs roughly $12,000 to $20,000 per kilowatt. The highest capital cost, but the highest density and the lowest operating cost per kilowatt once running. The critical insight is this: the cost per kilowatt of capacity goes up with liquid cooling, but the cost per kilowatt of actual compute delivered goes down because you eliminate thermal throttling, reduce fan power, and pack far more processing into the same building footprint. For hyperscalers building AI training clusters, the maths is simple. A building that fits twice as many GPUs per square meter, running at full speed without thermal throttling, pays for the cooling premium many times over. Neither, and both. The data center industry is not replacing air cooling with liquid cooling, it is layering liquid cooling on top of air cooling where the density demands it. Most new hyperscale facilities being designed today are liquid cooling ready. The pipework, manifolds, and coolant distribution infrastructure is installed during construction, even if the initial tenants are running standard air cooled workloads. When those tenants upgrade to higher density hardware, or when AI workloads move in, the liquid cooling infrastructure is already there. For enterprise and co-location facilities running traditional workloads, air cooling with modern containment and free cooling remains the most cost-effective solution and will be for years. For AI training, inference at scale, and any workload exceeding 20 to 30 kilowatts per rack, liquid cooling is no longer optional. It is the only path. The war is not really liquid versus air. The war is between the old assumption that a data center is a room you blow cold air through, and the new reality that a data center is a thermal management system that happens to have servers in it. That shift is going to redefine how these buildings are designed and built for the next 2 decades, and it is happening right now.